Good afternoon. Today we are going to talk about Spectre and Meltdown attack, and this is based on the ideas that I talked earlier on speculative execution, out of order execution, that architecture support for faster execution. And in the morning I briefly talked about out of order execution, where the micro architecture or this pipeline allows you to compute instructions out of their order. We also talked about speculative execution, where branch prediction allows us to execute out of order. And although these days pretty much everybody has a logo and presence in the social media, these are the first two attacks which has their own logo. And but these days pretty much every attack coming in, they have their logo, and as you can see Meltdown, it's melting works, and you can see Spectre, and as you can see by just by looking at it, this has something to do with twigs or branches. So, this basically exploits branch prediction, and this one exploits out of order execution. So, in layman terms, if you understood it, all I am going to do now zoom in and show how Meltdown uses out of order execution and how this one uses speculative execution. One more key point I want to highlight, both of these attacks were kind of created by Paul Cocker, and he basically did published around 4 or 5 papers and pretty much got all the awards available in the community, including National Academy of Engineering and Science. If you want to be researcher, become like him, not like me. So, not only Spectre and Meltdown, even remember we talked about power side channel attack. The first paper on power side channel attack was by Paul Cocker. He is the first one to come up with the idea that you can, by looking at the power, and then so many other side channel attacks came out, whole domain. Now, just to summarize where we were, Spectre basically whenever you have a branch prediction, if there is a true or if there is false, many architecture does many things. Architectures through predicated execution, Intel, it allows execution from both path, because it has so much resources, all the paths, all the statements in the if path, all the statements in the else path, it starts executing until it knows whether the condition is true or false, and whichever was false it will just eliminate those. But whatever it is, it executes instruction that it is not supposed to execute, and that is basically causes Spectre attack. And out of order we already talked about, if there is a instruction who is dependent and independent instruction you can execute out of order, that causes Meltdown. Any question on this basic idea? Out of order, Meltdown, branch prediction or speculative execution, Spectre. So, let us look into the Meltdown. Now, you cannot just do out of order on anything, now we are getting into the detail. Okay. So, everything written here, every piece of comma full stop is important here. Let me try to show you that. Remember we talked about this attack, we said we know the location, which location can be accessed first, which node we do not know the value of it. So, the location story, this move here is basically, this was the original code, I kept it out of respect, for us it is a load instruction. So, when you are trying to load something to a register from certain address, and that address through the attack, cache timing attack, I can figure out what address it is, but I still do not know the location of it, then the value of that location. The way we know the value of the location, we use same story, same load, use it as an index for another array. And the reason that works, if for this one you do cache timing attack, and let us say this location is what, let us just give it a name, 89. If this location is 89, then the story for this value, this byte x, this value is 89. To figure out the value, whatever location we figured out the victim process accessed, if that is the location I need to figure out, we use that location with another array, and whatever location becomes most recently accessed, then that is the value. So, it is not a coincidence this, and later within Spectre we will do the same, this and this is same. So, this one is going to create the condition for cache timing attack, then I want to figure out. So, basically think about it, I know this location, right. I create an array and access all the elements in that array, and only the kth location where I have this story, that k is actually the value of secret here. It is very simple. Take a moment, think about it, ask me questions. First time you attack, you get the data, then you find which location actually causing this, then create another array, big array where that location is one of the element, and then flash everything, allow the victim process to run this time, and then do this access. Whichever location, that location itself is the value, because the way we constructed this program, right. Okay. So, that is basically meltdown attack. It is basically information leakage. This category attack is called information leakage.
But how do you control the operating system to make this order of execution, like attacker, victim, attacker, right?
So, that we are not discussing today, but there are papers, there is also a vulnerable CVE entry. How do we do placement of, you choose your placement between accesses, how do you make operating system make you place, and in fact most of the time it is trial and error, and if you are not placed, that is fine, you try again, when you get placed then you mount the attack. Yes, please.
Sir, can you explain how we can assess the data?
What do you mean by access the data? It is still a load instruction.
Means no, we have loaded the first there will be illegal access. Then
this particular load gave you the clue, although this picture should have been two pictures, gave you the clue which location the victim process accessed, right. Then this particular load will go create another array with that location. So, let us say this one give you location, I do not know, 40, 50 or something like that, and then in the next one you create an array with more than that location and keep accessing, and whichever location comes in. So, here array is this byte x, here byte is this one, this byte is most recently accessed with this location as input, and that is basically the value of your secret. Play with this code, you will figure out. Now, next one I am going to talk about the Spectre attack, and Spectre attack, as you know, meltdown attack works only on Intel processor, at least the original versions of Intel processor when he came in, but this attack works on Intel AMD and ARM, and this operates on this principle. And the principle is, if you recall, what it is trying to do here, this branch prediction x less than certain size, this is the original code. You have to have a code like this in the victim process. You have to have a code like this. If this code does not exist, then you will not be able to mount the attack. Now, so in the attacker process, what we are trying to do, we are trying to insert a value x. Let us say this array size, I am just making it up, array size is 10, then I want to provide the array size of 40. Now, that has to be carefully chosen. That 40 address is not my address, it is some other program's address. I am trying to get to there. And in a normal situation, processor is not supposed to allow you to access this instruction, because 40 is not less than 10. But the branch prediction, which does not know any of this going on, and attacker has to train the, which I will show in a moment, attacker has to train the branch predictor multiple times by giving value of x less than 10. Give 1, 2, 3, 5, 7, 2, 3, hundreds of times give value of x lot less than 10. So, basically predictor knows, remember this is an instruction, let us say branch less than equal to, this has an address, let us say address is 80. So, branch predictor understood that last hundreds of times address 80 came in, it was taken. So, this time it is going to predict taken, although I am not going to get through that 2-bit predictor actually how it is implemented, that FSM, but think about it, previously hundreds of times attacker trained on location 80 or address 80, that instruction was taken last hundreds of times. Now, this time it is going to give a wrong value. and then this time it will be taken and these will be executed. All the values are actually important. This one is same as this one, that is important, and it should remind you how we did the cache timing attack earlier. So, we are creating a second array using the first array. This part is also important, this is the page size. If you are doing this attack on a different architecture, that has to be the page size. So, then once this setup is right, then you are basically going to fetch the data into the cache, and remaining part is cache timing attack. So, everybody begins with whichever way they begin. So, meltdown begins with out of order execution, Spectre begins with branch misprediction or whichever way you look at it, but end result is cache timing attack. Any question? So, end result is same cache timing attack.
So, here he is want to access array 2 or array 1.
So, remember in the previous meltdown example, this one if you try accessing, all you know that whether the location x was accessed by the attacker. You do not know the value of location x. To know the value of the location x, you have to embed in another array, do the full scan of that array, and whichever location is most recently accessed, then that is the value. So, it is the same analogy.
No, but you mentioned that your x is 40, right, which is greater than array 1 size. So, then array 1 x will give you illegal access, right?
It is supposed to, in general it is supposed to, but before any of those exception handling happens, you get the value in the cache, that is the whole idea. And most of these ideas are basically using this branch misprediction, that is also an exception, array bound, that is also an exception, everything is basically the exception handling takes time, and just use that as a window of opportunity. Any attack, you need to find a window of opportunity when somebody is vulnerable and create a covert channel, and cache timing, cache is the covert channel. I will zoom in little bit. Now, I want to just highlight Spectre attack is more dangerous than meltdown, because it has lot of wider attack surface. In fact, this is one variant of Spectre. Spectre has many other variants, and there are at least 2 CV entry I have seen. So, basically for Spectre attack, you kind of setup phase, you mistrain the CPU with speculatively the instruction. You just keep on running and train the then speculatively that leak information, all that stuff, and final phase you do cache timing attack. So, it has basically 3 phase based process, and so this is basically a little bit of zoom in what I already say. So, array 2 is readable by the attacker, and load array 2 and for all will be fast, and so basically again here there is a mix of things people did, prime and probe, evict and load. Remember all the cache timing attack, different exploration people did. So, what mitigation? First mitigation is just disable speculation, disable the out of order execution, but that is going to have really high performance impact. And then there are kind of compiler initiatives that basically looks at what are the sensitive execution path, and at least can you do halt speculation on the sensitive execution path. And then there are also, whenever there is a branch prediction, branch predictor table, flash it on context switch, because if you kind of do that, then this train does not think. So, if you can flash everybody starting with the cache, all these problem goes away, just flash. But flashing all these branch target buffer, flashing branch target buffer which maintains information of history is possible, it is typically 1024 entries, but flashing cache is kind of impossible, it is megabyte to gigabyte of space, and in every misprediction, and remember the pipeline is very deep, and then branches are coming almost alternate clock cycle, and even if you have a 10% misprediction and flashing takes like hundreds to thousands of cycle. So, you could imagine how much performance penalty it is. So, that is about Spectre and meltdown. Now, I am going to introduce another attack which is basically absolutely different from Spectre and meltdown. It is called microarchitectural data sampling attack. The idea is there are so many structures in the architecture, load buffer, store buffer. How do we basically use those buffers, or how do you misuse those buffers and their accesses to mount the attack? And for this basically, as I said, the attacks that have been published, people showed how do you attack the load buffer, how do you attack the translation look aside buffer. Recall we talked about virtual memory and mapping from virtual address to physical address. That is where all these mappings are kept, translation look aside buffer, then store buffer. And if you look at just the AMD processor, you will have load queue, store queue, the commit queue, and there are all these buffers and units. Those buffer, how do you utilize or exploit to mount an attack. So, let me just do the animation, so that you kind of see how do we do attack on AMD thing. So, basically you load, you want to load an address, all attack starts with load. You load an address, of course, the address we are trying to go after where there is a secret, otherwise who cares about that address. That could be key or anything that you are interested in, and that is not your space, that is not your user space, somebody else's space. And for corresponding to that, you might have a TLB, some mapping table, some mapping address, and a load store unit basically gets that particular address and the kind of value, and then cache gets those value. And so this blue color is basically the victim, this brown / maroon color is basically attacker. I am just trying to show now the attacker needs to come in, attacker need to flush the cache, and attacker flush the cache, cache is clean, and at that point attacker load the address, and then attacker basically got that a TLB hit, that page has already been brought to main memory, not in the cache, but it is in the main memory. Then it is load store unit, and then it basically speculative load forwarding it does. Remember that array of address to, first it did load address to, then array of address to. So, at this point basically array of secret it got in, and it fetches to the cache, and then basically you, when you reload, you basically look at the time of which of those locations are getting faster, and that location is actually your value. Yes, please.
So, in your meltdown example, you mentioned that
out of order.
Okay, no, it is meltdown. So, in Spectre, I have a question. So, your array 2 is also a victim's array, right? So, you cannot access array 2 also.
Right, but the assumption is attacker can access array 2.
But if it is from victim data, how he can access?
Now, that data that is for victim is this one. So, what we are trying to do array 2 so array 2 this particular address, right, there are two ways to look at it. One assumption is this array 2 is in the no, array 2 has to be in the other person space, but because of speculative execution that data comes in, otherwise this data will never come in.
Program, you should not put array 2 in the code, it may be something else.
Yeah, it could be any name, but the key idea is wherever you are trying to look, this name has to be same, whatever first load you issue.
So, that understood, but array 2 may be attacker data only, he just want to access with that particular
data, that data like and this address, but the still catch is array 2 is in attacker space, but array 2 this location is not in the attacker space, out of bound space basically. So, then even in here basically when you kind of mount the attack, you are able to find. So, as you can see all the attack, I will show one more attack actually, you will see all of them one thing in common: create some exception, create a window of opportunity, bring the data to the cache, and then do the cache timing attack. Because I am using cache timing attack as the side channel, there are, as I said, there are other side channels even microarchitectural family. Now, how do you mitigate? So, there is an instruction called lfence. So, lfence basically selectively cleans, you can think of layman terms, selectively cleans some of the locations, for example, translation look aside buffer, store buffer, and so on and so forth. So, then if you do lfence, wherever we are able to find this access time, lower access time, that thing does not happen in once you do the lfence, because it is clean that stuff, some of the stuff it cleans, some cache controller and all that, but it is a huge overhead. And also there is the understanding of where do we put lfence, right. Sometimes people say, oh, between after every load, but after every load you put in, Of course, the idea if you put after attacker's load, that would be nice, but why would attacker put a elfence instruction there, right. So, in the victim space, if you kind of put a elfence there, I mean victim does not know anything. If I am loading some data, so it's sometimes it's kind of tricky, but typical idea is anytime there is a load or speculative load, then you kind of do elfence. So, then some people will say, why do you do speculative load in the first place, just do not even do it. So, either way elfence is actually the solution for Spectre, Meltdown, anything that ends with cache timing attack. Elfence basically solves those. Now, I am going to talk about a recent one just to show you something funny. We talked about assertions, right. So, we introduced the idea of adversarial assertions. If assertions exist, remember I said any microarchitectural feature you have seen, for everything attack is possible. I looked at that spectrum and I saw assertions, nobody did any attack. Let us come up with a name adversarial assertion, and in fact, my next paper name itself is adversarial assertion. So, the key idea is the same. We are using exactly same, and in the attack community they are called as gadget, microarchitectural gadget, and that gadget basically in the victim process will have assertions, right. Now, it is kind of a little tricky that and those assertion and there is some secret. Objective is I kind of want to have access to that secret through the attack. Now, when victim process inserts the assertions, assertions create vulnerability, right. That was my first objective when I introduced this idea, and assertion is nothing but a if statement. I want you to understand, it is nothing but a if statement, and if it is an if statement, then n missing. If it is an if statement, then basically the branch predictor, same mistraining, same Spectre attack I can do. Assertion, when it fails, if I as an attacker somehow make this assertion fail victim process, or I have to wait when it fails, that creates an exception, handling of that exception when it fails, then that I can use the exception delay. But no matter whether through branch prediction or branch misprediction or exception delay, I create speculative execution, I can do timing attack. When I thought about it, then I thought it is exactly same as Spectre attack. Then I ran through basically the spec fuzz. So, this is one of the tool that basically runs through your design, and I talked about different testing technique, and fuzzing is one of those technique. It is in a way you can think about it is a random test pattern you run and check, but only difference with normal testing is it remembers what happened in the past. First you ran 100 test cases, what happened? It maintains a history of success and failure, that is the community of fuzzing, but in layman terms it is basically run lot of random tests, but it is just that you remember what happened. So, then you guide it in a right manner. In normal testing based validation framework you do not remember anything. But anyway, so we ran this spec fuzz, it could not detect because it did not know assertion could be a problem, it is just legitimate instructions. But so that is basically kind of thought, and but just zooming in, it should not be a surprise to you that the kind of sentences we are putting here, it should resemble you to something. So, when we talked about this if statement and all that, this is for speculative execution if you recall, but of course, we multiplied stuff by 4096. So, if statement is nothing but assert. We can kind of do an assert on buffer size, we can do that, and corresponding code if you look at it is pretty much kind of similar, slightly different. But the key idea is the victim function needs to have a code like this. Now, how do we make a victim write code like that or not, that is a different story, but because just having an assertion is not going to help, it has to have assertion, something you have to have some knowledge about victim's code. And as you can see, the next one is exactly same as, so this whatever you are doing array 1 size, this is that array 1, this is array 2, this is page size. So, this kind of code has to be there, these are the gadgets, if this code is not there you cannot attack, but once you have that, and so then branch predictor I can write a for loop, and that particular assert for the x value x that I want to mistrain, I can basically that function I can call many times, and it is going to be trained to be taken. Once that address comes it's taken, then we need to call victim function. So, now I know the way I wrote as if me as an attacker can embed victim's call here, I mean that is not going to happen, right. So, this is like one iteration of attacker function, then victim function, again one iteration of attacker function, then victim function, you have to do that chain series. But I simply wanted to show how if you can put victim function inside, how would it work. And so, basically assertion or branch condition, this pass fail. So, basically 1 to n times you want it to pass. So, that branch predictor, the history it maintains when this address came in, although that is not technically accurate, think of for every address in the predictor it remember, every time it successful it increments a counter, every time it fails it decrements a counter, but that is not how it is implemented. So, basically if the number is large enough, positive number, then you know it is taken. So, that is what you do, you increment the confidence of the predictor by n times, and then when you mount the attack it is still going to predict taken. That is basically the key idea. And this exception assertion is going to fail at some point. Remember when we talked about assert and file pointer, if file pointer is null it is going to fail. Similarly, whatever condition the victim process failed inside the assert, that condition when it is not true is going to fail, and when it fails it is going to, an exception handler would be called, and that is the window of opportunity for the attacker to basically do whatever it wants to do, bring stuff and all that stuff. And so, basically, so this is basically the exception handling, the kind of function call that gets called. So, you have to have a knowledge, if you want to do this kind of attack, you have to have a knowledge what exact exception handling routine operating system calls, and how much time do I have, what are they trying to do, which one they disables, which one they enables. So, that is basically the story here. Now, if you see, once we apply, we can find the locations. Earlier I was talking about one secret, this time I am trying to see 1, 2, 3, 4, 5, 6 secrets. Can anybody tell me what is this secret I am finding here? The data in those locations, the way we created this, 65 is the ASCII for A, 116 is ASCII for T, it is actually a attack, ATTACK. That is the word that we are trying to figure out, right. What was this? That is the secret word. But so, with 6 bytes we assume that as a secret in somebody else's space, and we are trying to figure that out what the 6 word is. And as I said, LFENCE works everywhere, LFENCE also works here, and as you can see, even if you have one data, LFENCE when you do it basically kind of, it does not create any entry that is faster access or slower access. Any question on adversarial assertion? So, the way I chose all of those, so that you kind of see its starting point is same, end pointing same, key idea is exactly same. Bring the secret or the location or the value from some location, you are not privileged, you are not allowed, not your location, into the cache, followed by mount a cache timing attack. Okay. So, now the interesting part, now that we know what these types of attacks are, now how do you use explainable AI to kind of detect those. So, what exactly people do today to detect? Remember, there are two types of mitigation. One mitigation is my favorite mitigation is empty the cache, context switch, anything goes wrong just go and clean the cache, or if possible just shut down, restart, whatever it is. But these kind of mitigations are kind of performance degradation, huge performance degradation, 2x, 5x, 10x is performance degradation. And of course, this mitigation also kind of includes the disable everything, speculative execution, out of order, branch predictor, disable everything. If you disable branch predictor, then every instruction you have to wait. How much you have to wait? That depends. Every instruction you have to wait at least for one cycle for the decode to realize it is not a branch. If it is a branch, you have to wait longer. If it is unconditional, then target you know after decode. If it is a conditional, you have to wait at least one more cycle for execution, you need to figure out the condition. If it takes longer, you have to wait. So, you have to wait at least one cycle, maybe 2, maybe 3, or depending on the size of the pipeline after every fetch. So, you cannot fetch an instruction every cycle if you want to disable branch prediction. So, everybody you want to so if you have to wait at least one cycle every time, that is a slowdown of half. If it was operating at a gigahertz, now it is operating at 500 megahertz effectively. So, mitigation is one approach, then another is the detection approach. We will use whatever is running, but we want to detect if the attack going on, and if attack is going on we want to basically stop it, pause it, whatever you want to do. If attack is not going on, then fine, everything goes as usual. This is same as the virus detection we have talked about, malware detection. Remember, Spectre, Meltdown, these are actually programs. You can view them as malware, but technically that is not how it works, right. It is not the software is doing all the stuff, it making use of architectural features. So, there are many ways of solving this hardware performance counter, machine learning. As I will show you, there is a high false positive rate, and high false positive rate basically many times it is going to detect a legitimate execution as a Spectre attack or Meltdown attack, for example. So, just to kind of motivate, let me go back to what we already discussed earlier. So, when you run a machine learning tool, this is pretty much what it does. In this example, I simplified it to 3 features, 3 of the good features: branch miss rate, and it should not be a surprise to you why branch miss rate came up one of the top features, because speculative execution rely on branches. So, it has to be something about branches. Then lower level cache misses, cache timing attack or bringing to cache is the issue. So, cache accesses and cache misses, those are the features. Now, anybody remembers where these features comes from? Every processor comes with hundreds or 200s of performance counter, where it computes and maintains what is going on. If you executed a program for 1,000,000 cycle, you can know how many of them are add instruction, whatever question you want to ask, pretty much they maintained all of them or most of them. How many branch instruction, how many of the branch mispredicted, up to that point, up to that point. You can stop anywhere, you can start anywhere, you can reset anywhere, you can restart anywhere. Many of the compiler researchers, what they do, so many of the compiler researchers, the code basically wherever they kind of put those accesses, they might reset the performance counter when they feel like. Then they have some code, and then they just said, okay, count the number of cache misses, the cache misses, that counter it basically prints. So, then if you print that, for example, every for loop you are printing, what you want to do with it is different, but I am saying if you want you can print. Only catch is you cannot run this program in normal mode. Performance counter access only is in super user mode. Even this detection I am talking about, this has to be in super user mode. You are running in your company server, you will not have super user mode. So, then you will not be able to run this, or this embedded code is not going to run, you will not have access to performance counter, right. I mean, some of the system things you can do even in this mode, like you can get the time function call and few other stuff, but when you want to do any of the hardware performance counter, that access, that is one thing. Second thing is, if you put too many of them there, then it is going to slow down your program execution. In fact, performance counter is nothing but a function unless it is implemented in hardware, that also will have cache misses, cache hit. So, it is a lot of complication. Now, can anybody tell me why am I talking about embedding, give me number of cache misses, give me number of cache accesses, and how to embed, why am I talking about it? Because for, yes please, to train the AI model, because for machine learning to work, for a legitimate program you need to embed, get the data and tell the AI, for this program the data I am giving you, that is a good program. This program the data I am giving you, that is a Spectre attack, known Spectre attack. So, you want to train the program, right. Let me so, as you can see, if you kind of train, and then as you can see, most of the good programs are in this space, which basically is high cache miss rate and I do not know lower, whatever it is, the branch miss rate is very high compared to the one that has malicious or Spectre meltdown kind of things. So, as you can visualize, although there are few dots here and there, you can visualize machine learning tool builds some kind of boundary kind of like this somewhere. Next time you run another code machine learning tool, by looking at these 3 parameters, try to see where you are. Let me just plot it, some number somewhere. Let us say if the number is coming here, then you know it is kind of malware. If number is coming here, then you know it is a normal execution. Now, when you run this or do this, what is going to happen? Most of the time it is going to make a mistake. Its false positive rate is basically, it is going to talk about most of them as in this community it is inverted. When somebody has a cancer, we basically say test is positive. So, positive is actually negative. People do not want to have cancer, but that is the positive. But if somebody does not have a cancer, but prognosis says you have a cancer, that is known as false positive. False positive is good there, but either way. So, some of the good one you are trying to say as malware, runs Spectre and Meltdown is not a great idea. You turn it off, shut down, clean, that you do not want to do. And so, basically anybody knows why it makes so many mistakes, but the structure looks so good. Why does it make so many mistakes? Because maybe I will ask this question later, why the solution I am going to show you, why does that work? Because that solution is also use hardware performance counter. Then how can you say it does not work and work there? So, that I will come to in a moment, but then there is a bigger problem. Now that attacker knows you are using these as parameter, it is going to put bunch of if statements there, it is going to train the branch predictor as much as needed or whoever needed to create a situation like this. So, here the green dots here are evasive Spectre and Meltdown. So, Spectre and Meltdown that knew how you are detecting, it created bunch of fake stuff. So, as you can see this structure is nothing but take some of the red dot, push it up through this parameter, and that is what it did. It is just not put it up, it is all over the place. Now, in this picture the perspective I am showing, maybe it looks all surrounded. If you kind of rotate or look it from another dimension, there might be plane, but I still wanted to highlight the point. Once attacker knows how you are detecting, which features you thought as important, they can play with that feature. That is called evasive attacks. And same analogy I forgot to talk, even in malware same thing exists, evasive malware, they also known as metamorphic malware. The idea is if they know your detection technique, they will try to evade that detection. Any questions? So, now your normal machine learning tool will get confused. Ignore the red dot for a moment. Now, think of differentiating between those the green stars and blue crosses. It is just all over the place, you do not know where to draw the line. Now, it is quite possible we did only 3 parameters, 3 dimension 3D. If you had 4 parameters 4D, 5 parameter 5 dimension, then maybe it might become visualizable. So, I am going to show you a solution that makes use of hardware performance counter and addresses this problem metamorphic and produces nice results. Before I show the solution, I wanted to hear from you, why would it work? No matter what you do, why would it work? Same hardware performance counter, same set of values. Remember, hardware performance counter implementation comes with the processor. You who is implementing a detection solution, you do not have the ability to modify those counter or do anything. If you can modify, then you can have a different solution, right. So, this technique uses something called the idea of time sequential data. So, what does that mean, time sequential? What does that mean? So, basically take any of the number, let us say branch misses, right. Let us think of branch misses. So, the reason other people make mistakes, because they focus on what is the total number, let us say 100. What this work wanted to do, what we looked at, we said that is why the problem 100, everybody going for the overall statistics, that is a problem. Instead, what we should be interested, how many branch misses between time 0, I am just making it up, 0 and 10, how many between 10 and 20, how many between 20 and 30. So, maybe this is 5, this could be 7, this could be 9. So, that basically this delta is important instead of looking at the total number. So, series, and in fact, and it is actually not an innovation in this work, because in security domain most of the data is actually time sequential data. That is why neural network is not a good idea. And as you should be obvious to you, what do you think is a right machine learning model here? When you have a series of data, or community calls it time sequential data, series of values, this case it happen to be branch misses, it could be anything, series of values over a period of time, some value, LSTM is the solution. So, basically any form of recurrent neural network would perfectly fit that story, any form of recurrent neural network. So, then data collection, as I talked about. So, couple of things is needed. You need the data collection, you need to train, and of course, you need to test to check how good is your ML model. But the key idea is, when you make mistake, what do you do? That is the explainability. When you make a mistake or wrong prediction, what do you do with it? That is the key idea. That is the, so that explainability aided. So, this is the part where explainability basically comes into the story. When you make a misprediction, so then two difference compared to what people are doing and making mistakes, instead of using overall statistics, how cache misses, how many cache hits, you consider the difference or the cache misses over a period of time, how many in first cycle, first 10 cycle, first 20 cycle, that is time series data. So, time series data, and in fact, all security solutions time series data is crucial. That is where neural network is not used, or convolutional neural network. So, data collection is important, that when you run the program, this performance counter collection, you can instrument the basic blocks, right. So, for your testing and training time, so it is the training time. The attacker will not allow you to embed something on their code, right. So, that time you have to rely on what your machine is giving as the performance counter. But when you train in your program, you embed those performance counter calls, every basic block in 10 basic block, depending on what and what frequency you want those, and you have to make sure, because of you embedding the performance counter calls or too many of them, that does not change the behavior of the program, except performance, does not change the behavior, does not change the performance counter values itself, because you call too many times performance counter. So, that is how you kind of generate, and then different kind of events we kind of observed here, total number of instruction, total page fault, branch, misprediction, cache misses, cache accesses, and you kind of look at, and it should not be a coincidence that Spectre, some of those are kind of relevant, Meltdown, some of those are relevant, and you kind of want to, depending on what you are activating, you need to have lot of events. And in fact, if you put 20 events or 30 events, give it to Shapley value analysis, it will do the ranking for you, it will tell you which one to use. So, you can do a pass of that, then you can go with the second pass, but either way data collection is important, right. And another important part is, this has to be a on time detection. Whenever things are running, you should be able to tell there is a problem, but I am still talking about the data collection. And as I said, recurrent neural network, and we essentially used a variation of it, long short term memory. Recurrent neural network, the way it is designed, it actually naturally captures time series data. So, that is basically the ML model. Now, in terms of model training, so model training basically, as I said, for each of the parameter, number of instruction, I do not know what these are, cache misses, cache accesses, different time frame, again this granularity matter. If you use very fine granularity, your accuracy would be higher, but the collection time, training time, that would be humongous. But different time series you are putting, remember the delta is basically how many instructions got executed in this duration, there would be a table of that. That is the table you give as input, and then you basically the recurrent neural network, in this particular case long short term memory, we kind of train, and then you push it through in our case we used it multi-layer perceptor, then softmax layer, and we basically get the model. And this particular case we use gradient descent at the end, and you do this until convergence, the typical machine learning stuff. This is the exact code, and again this work was like few years ago. Today with the newer PyTorch library you will be able to do even better, there are even better functions. But nonetheless, this is the idea, and this is also important, which was not in the previous picture, because you have to kind of do the gradient. Remember we did gradient descent even in other optimization problem, you kind of do gradient descent, get to the point where it kind of converges and then your model is. So, the key idea is in the gradient this in the ML community it is a loss, for us it is making less and less mistakes, it is giving more and more accurate results through the steps. If it start giving more and more errors, then you are not going in a right direction. So, once we have data collection model training, now the question is, of course, this part I did not spend time earlier. If you ignore explainability for a moment, most of the other machine learning applications, once you do this, people do not mind how long you take, people do not mind, they will not ask you a question. But once you kind of have the trained model, people want to know the accuracy of your model, and when you test accuracy, you have to test with the testing sample, and this sample should not be part of, they should be mutually exclusive. As a researcher, what we do, whatever data we collected, we typically do, my group we do 80-20, people do another. So, you kind of collected some data for 100 whatever randomly whatever you did, 80% of the data you use for training, 20% of the data you keep, you do not expose to this one and you test on this one, that is basically how people do. And these days there are a lot of other ways of people talking about, oh, this is still not fair, your data generation was done exactly same way, it is the same design, same stuff. So, of course, if it was trained with this data, when you test this is going to be great, but as I said, things are changing, and what reviewers used to think as acceptable does not think that acceptable anymore, you need to just stay with the current policy. But this is the testing part, earlier I did not talk about, I want you to know this part is important for publication. You keep certain part of the data, you test it and talk about the accuracy you print on this one. Of course, this one will have 100% accuracy, this better be 100% because you do it gradient descent and it converges, that basically means this is supposed to be 100%, nobody cares about that number. Now, I am going to talk about, now that you have the ML model, whatever it is, the LSTM, whatever the structure, think of that curve or slope it has created. Now, it made few mistakes, right, it made few mistakes. How do I fix those mistakes? The result it provided, how do I interpret those and what do I do about it? So, this one I am talking about the explainable. Last time I spent lot of time on Shapley value analysis, this time I am going to use this part, this story for another explainable AI model which I briefly introduced called model distillation. So, I am going to show you in model distillation. So, model distillation in layman terms, you have the original model and then you have a distilled model. So, basically they work together to give the prediction. Now, distilled model may not be physically separate model or it may be same, it could be merged, but whatever it is, that is the idea. Let us look into what do we do that. So, this is again just recap what is explainable machine learning for model distillation. So, you still have the original model, so far we basically trained this one. Now, this distilled model based on the mistakes we kind of did, we are going to do retraining. Of course, retraining is going to change a little bit of the original model, but distilled model is going to try to capture more to figure out who is most influential. Now, so result interpretation I am going to skip all these things. The basic idea is whatever data it produced. So, explainability gives you something like Shapley value analysis, model distillation also gives you a value depending on what feature you used for space. So, when it gives a value, here we see clock cycle 4, something is important. Now, this is also important for debugging, and in fact, the way if you do this as a feature vector, this is the value you get. If you use register or variable values, I am just making it up, let us say this value is also high, there will be a list of values, let us say this value is also high, then you know something is happening in register 3 content at time step clock 4, right. What do you want to do with that is different, but that basically helps you in kind of doing. And then when you this particular example, what we looked at, because if you ignore explainability for a moment, let us think about how do people do when they made a mistake, what do they do? When they made a mistake, anybody knows, non-explainable AI, how do people take care of it? During training time. During training time they made a mistake, they found a mistake, or during testing time, forget about training, during testing time they found a mistake, what do they do? One of the cat came as a dog, what do they do? Retrain with what? Remember, input is cat and dog pictures. What do I retrain with? More of the kind of pictures where it made mistakes, and this is known as adversarial samples. Although the word adversary, there is no attacker sitting there. It is just that wherever I made a mistake, a cat for some feature look like a dog, it made a mistake. So, that kind of picture you train, you kind of retrain. Now, how many, what, how do you get adversarial samples? That is the difficult proposition, and in fact, in this particular case all I am going to tell you that how do we compose those adversarial sample by using explainability. So, if explainability is not there, you basically one picture it made a mistake, you just try to push so many of them, you keep running, you just try to push those lot of those type of picture. So, it is kind of an ad hoc process. In explainability, in this particular example, we kind of tried something like this that worked called data augmentation. So, basically first of all remember machine learning told us it is an evasive sample, right, and then or wherever it made mistakes. So, basically in that evasive sample, these are, think of these are the basic blocks on that code, that Spectre, Meltdown, whatever code. These white boxes are basic blocks. Think of basic block, although there is a standard definition, bunch of instruction, no if coming in, no control going out, no control coming in. So, that those instructions. So, those blocks that are not relevant for the attack, some normal stuff, but these red ones are actually contributing to the stuff that eventually somebody will use as a cache timing attack. So, those are the important one in a evasive sample, and here is the original sample, and even these are not important, these white ones, but these ones are important in the original sample, something distinguishing. Now, normally it may seem like, well, in original sample none of them are detrimental anyway, but remember victim wants certain type of code to be there in the attacker wants certain type of code to be there in your code, so that it can mount the attack, right. So, those are that is what I meant by important blocks, important for that attack. If it's Spectre different, it's Meltdown different, but those are the important blocks in the original sample. So, we have done lot of stuff, and these kind of ideas exist in all explainability based solution. People somehow try to come up with new sample. So, basically we came up with the idea of this padding. So, we can add some random blocks, we did some inserting, in the random blocks we inserted some of the important from original and important from the attacker blocks, then we kind of permuted some of them left and right. So, that is basically the final sample that I want to train with. Now, we can do so many ways, each of them has their own pros and cons, but I want to ask a simple question, why are you doing all this stuff? If the solution where it did bad, why did not you create bunch of those, a lot of those? If you take the cat picture, why did not you run a lot of cat pictures? Let us say these evasive sample, it kind of failed. Why did not I just do more of these red blocks and kind of pushed it in and feed it and train it? No, it is not the time, because first we are not using explainability. Second is, if you wherever you made mistake, if you feed a lot of it, that causes the overfitting problem. So, then all it learned, then I made a mistake, you beat me up, sure I will not make that mistake, but I actually did not learn the art of not making mistakes, because there are other possible mistakes I could have done that you have not seen, nobody has seen. So, all of these things are theoretically has shown this inserting, padding, permuting, putting random blocks, they actually minimizes those issues, those false positive, overfitting and all that classically known problems. So, these are the kind of solutions, and once you get in try generating synthetic samples, you will get to some of these terms, how and what, how do you apply that story to in some other domain, but the key idea is how do you generate samples, new samples based on where it failed. right. So, this is basically the data augmentation part. So, the key idea is because it is a model distillation, that is why you eventually have to call the distill function, but if it was Shapley value analysis, that is different. But this second part of the code is basically your training, and so you kind of have all these features, you sort them, you craft the sample. So, the picture animation I have shown, that is only this particular line, how you are crafting the kind of examples, then you add with the whatever previous thing was there, then you retrain, and then you kind of do the model distillation, distill, and then assumption is if you do it right, now your accuracy is supposed to go up, which I will show in a moment. But I want you to absorb this code and ask me any question. You originally have a set of samples on which you trained and you made some mistake. Now, you created new sample based on your mistakes, whatever you learned, you put all of them together and you retrain the system, and you still have to do then you do kind of model distillation. So, I want to show some results, and to kind of create results we have different categories, how obfuscation, non obfuscation. Let us go straight to the result. So, I want to highlight few things here. So, I am going to show you meltdown, and whenever you publish paper you have to figure out who is the latest work. At that point latest work was, let me see what was the RDSM, stands for something, real time detection of spectre and meltdown. So, that was the RDSM. Now, we gave benefit of doubt to the authors, because RDSM was built on top of overall statistics. So, we gave it a benefit of doubt on time sequential data, and then now you see meltdown performance is really high, 93 or even the modified version 95. But the problem is when you do evasive meltdown, that is a serious problem. 19% is kind of worse than random guess, right. So, that is a serious problem, and so evasive meltdown, right. So, basically, but if you kind of look at the diagram that I have shown, that even for evasive meltdown. So, when I say evasive meltdown, this is also after retraining. After retraining, this is kind of that bad, but the advantage we gave, that is still a random guess. But here sure detection rate whatever accuracy was 99, it went down, but it is not really that bad. Of course, false positive, false negative are fine. So, the key idea here is that there are existing approaches that can do an amazing detection, but once you introduce evasion into it, by knowing, assumption is attacker knows what your detection model, by knowing if I can change my program, then the detection accuracy goes down significantly. Even if you retrain, whatever you do, it is not going to work. So, then explainability can help, that is for meltdown. For similarly for so different strategies and all I am going to ignore. Similarly, for Spectre, same story, and we have seen similar kind of thing for malware. So, detection rate for, so RDSM again the one, and then for Spectre there is also another algorithm, that was OSDA MLP. As you can see, RDSM is 89%, which is not that great, or even benefit of doubt is this 99%, that is like as best as it can get, and in fact our detection accuracy is less than that. But the problem becomes when you kind of have the evasive Spectre and meltdown, then detection accuracy goes down, and which is basically unusable detection accuracy. So, that is basically our also going down, but it is still reasonably kind of high.
So,
yes, please.
In this kind of ML based attack, how do you determine who is the attacker? Because there are many processes running, many user using the machine, right?
So, for the experiments, we kind of have those attack examples which is in the testing set, and that is basically the attack examples, exact Spectre attack, exact meltdown attack. But in reality it is basically same as antivirus check. You have your checker running and anything can run on your program, and when they are running you detect whether that program is a malware. This could be viewed also as a malware, although technically it is not a malicious software, it is basically a legitimate software taking advantage of microarchitectural failure, but basically you are trying to see whether this program is trying to do Spectre attack or not. That is the objective. And so, I am going to skip all of this stuff, and that brings me to the end of the morning session. Thank you. See you at 2 o'clock.
One questions.
Go ahead.
So, whenever you are taking performance counter, so in general performance counter people take by running with less load. So, underloaded conditions, only the victim program runs and other things do not run. Whenever it is overloaded conditions, how will take care of that issue?
Right, very interesting question. I did not address that. So, the question is this performance counter that we dump for during the training or during real time detection, we are relying on performance counter. All of these works amazingly well if whatever program you are running, victim, attacker, if one program is running, then the performance counter values are absolutely accurate. If multiple programs are running, context switching and all that going on, then it is not accurate. Now, that problem exists everywhere. Even when you do power side channel attack, when you dump the power traces, our assumption is only the program for which we are trying to do, let us say malware analysis, only that program is running, nothing else running. In fact, this problem is even bigger for electromagnetic emanation. When you are holding a probe, you expect only the logic that you are trying to see Trojan or not is running, but there is so many other logic running to make this logic running. Lookup table, controller, router, even the transformer, there are many micro transformers there, they also would be dissipating power. Even the voltage regulator would be providing so much of electromagnetic emanation. So, there are mechanisms to filter that out. And the last I checked hardware performance counter, you can actually mention which process you want to monitor, from which time frame to which, that slows it down even more. So, then it would tag on a process as much as possible. It would be still influenced, still there would be bias, but it is not going to count the instruction of other processes. You could do that. Any other questions? Thank you. See you at 2 o'clock.